Let's now take a look at the ball that undergoes horizontal circular motion. This ball, weight mg, is connected to a weight, capital letter mg. This weight here provides the tension in the spring that pulls the ball. So let's take a look at the vector diagram on the ball. There are two forces acting on the ball. One is the tension. The next one is its weight. So by drawing the vector diagram, you have your tension and your weight. And the horizontal circular motion indicates that the net force or the resultant force is directed towards the center of the circular motion. Remember when we earlier derived the acceleration for circular motion? The acceleration is always directed towards the center of the circular motion. And the force will therefore be directed also to the center of circular motion. And the force is called centripetal force. And the acceleration, we also term them as centripetal acceleration. So Fc, the centripetal force, is the net or the resultant force of the tension T and the weight mg. So drawing the vector diagram, this will therefore be the vector diagram where the direction of Fc is horizontal as indicated. So from this vector diagram, we can then formulate two equations where T sine theta is actually equal to mg and T cos theta is actually your centripetal force, which can be expressed as mv squared over r or equal to mr omega squared. If we divide equation 1 by equation 2, we'll get tension theta equal to gr over v squared. And typically in any of the calculations, this will be the formula that will be required to be used for calculations of a body undertaking horizontal circular motion. We could also take equation 1, we square it, and to add with equation 2 when we square it. By doing so, we are trying to use this mathematical technique where sine squared theta plus cos squared theta is 1. So in this case, since we add this as indicated, then t squared sine squared theta plus t squared cos squared theta is actually equal to t squared. So from there, we can make t the subject and we can square root this expression here. And in these questions, the tension T is actually equal to capital letter mg. So if we place mg inside m, the capital letter M is equal to this. A popular question to be asked is what happens if we decide to increase the tension? So if we now increase the value of your mg and your tension also increases, then we need to take note. Then we need to note that the magnitude of your weight of the ball remains the same, but the magnitude of your tension becomes longer. So therefore, because of this, we will have to do something. We will have to sketch the vector diagram as such. Let's take a look at the first scenario. What happens if we increase the weight, capital letter mg, and in turn, that will increase the tension that's exerted on the ball in circular motion. So when that occurs, the first thing we need to do is to take a look at the vector diagram. The mg, the weight of the ball has not changed. So the magnitude of this should remain the same. However, the magnitude of your tension will now have increased. But you have to take note that Fc maintains its direction to be horizontal. Hence, because of this, and since the tension is now longer, this will be the new vector diagram. From this new vector diagram, there's actually two conclusions we can draw. The first conclusion is obviously the centripetal force has now increased. The second conclusion is that the angle theta, which is originally here, has now become theta prime. The angle theta has dropped. Since the angle theta has now decreases, we will now have to have the ball in this manner. So the angle theta prime is here. So as you can see, when the theta decreases, we expect the radius of the circular motion to increase. So this is derived from the experimental setup. And finally, from the equation 2 or 3, you can see that in equation 2, if Fc were to increase, then and R were to increase, then obviously V must increase. Or if you take a look at equation 2, if tangent theta drops and your R increases, your V definitely must also increase. So both point towards the fact that V actually increases. The final part the final bit is for us to think about whether does the angular velocity increase or decrease. There's a counter argument to this. If, for example, the angular velocity of your ball has increases, all right? If the angular velocity increases, then we know that your FC would have increased. If your FC has increased, the magnitude of your FC would have this line would have lengthened, like what we have drawn here, and your tension would have increases, like what we have drawn here, and the angle theta will also decrease as well. So because of this, we conclude to say that the angular velocity will also need to increase. Let's now take a look at scenario 2, where in this example, what we have is that we increase the weight of the ball. So if you increase the weight of the ball, you will find that the weight of the ball represented in the vector diagram will now increase from mg to mg prime to m prime g. But the tension remains the same because the weight of mg did not change. So if you have the same length and you need to be able to form a right angle triangle with the centripetal force still in the horizontal direction, then we have to move it down. Once we move it down, we can then have our new vector diagram with the FC prime in this direction. So the conclusion from the vector diagram is that the centripetal force has now decreased and the angle has increased from theta to theta prime. So the angle theta has increased. So looking at the experimental setup, in order for the angle theta to increase, the ball will now be actually at this position, which means the radius of your circular motion would have decreased. And in the same way that we analyzed for the earlier scenario, if you look at equation 2 and 3, if your FC decreases, your R decreases, then your V must decrease. If your theta increases, your R decreases, then your V must also decrease. And also in terms of angular velocity, we could also argue to say that if angular velocity were to drop, then we expect FC to decrease. If FC were to decrease with tension being constant, we will still end up with a conclusion that this is actually the vector diagram, which means we will also conclude that the angle theta will also have increased. Hence, because of this, the angular velocity in this scenario must decrease.